Afternoon session. So we will start with André Belotto that will explain something about resolution of foliation using principalizations.
So thank you very much. So I would like to start by thanking the opportunity to give this talk at this conference. It's a great opportunity to speak at your conference for you, Frank, especially. I still remember the first time that I gave a talk where you were in the audience. It was in Rennes. And I was just finishing my PhD, and I was extremely nervous. There was you and there was Cerveau. And I was talking exactly about this. But not yet the global result. So I'm going to talk about it, because I was talking about this. So let me start. So today I'm going to talk about resolution of foliations via principalization. And this is a joint work with Abramovich, Temkin, and Wlodarczyk. So let me start by just giving you some setting and then talking about, I'm going to state the theorem quite early in the talk. So for me, for this talk, I'm going to consider X essentially is going to be a C analytic smooth variety. So by this I mean complex analytic space. Okay? I'm going to consider this as my main setting. It could be algebraic. I'm going to avoid the world of algebraic simply because I want to use, we're going to work with foliations. It's just much more convenient to state results using the Euclidean topology than to talk about étale morphisms. I want to avoid all of that, so I'm going to stay here. But you could work with any algebraically closed field, a variety, a smooth variety over any algebraically closed field. And at some point, instead of a variety, I'm going to work with a von Orbifold. Or a Deligne-Mumford stack. Smooth, always. And in this kind of setting, I just want to recall the classical theorem of Hironaka, right? There's a classical theorem that in the analytic case is due to Hironaka, Aroka, and Vicente. And that states the following. So I'm going to take here a subvariety of X, which might be singular, and we're going to be able to find a resolution of singularities of it, of an embedded resolution of singularity. So I'm going to find a proper binomorphic map here, which is defined over the ambient space, X, in such a way that when I consider so first of all, this pi is going to be locally. Because I'm analytic, I need to talk about something which is locally. I cannot give, this cannot be given by just a finite sequence of blow-ups. But locally, it's a finite composite of blow-ups, just as we are used to, in such a way that the strict transform of the subvariety is now going to be smooth. And moreover, this process can be done in such a way that the choice of this morphism is canonical. That is, it does not depend on coordinate system. And it's also functorial in respect to smooth morphisms. So these are technical properties. I'm not going to enter too much in details. I'm just going to make one comment at some point about this, because it's going to be important to understand why the case of orbifolds is actually not more harder than the case of varieties. And this is going to depend on the fact that it's going to be functorial. Now, this statement, as given here, it's not, usually we want more control. We want to have control about the transform not only of y, but over the singular locus. So this usually is given by the control over an exceptional divisor. So E for us is going to be a simple normal crossing. So SNC, simple normal crossing. Divisor. Let me start here by making my choice. So E for us is going to be a simple normal crossing divisor. So this just means that, well, at least in the analytic case, it just means that locally, this divisor is going to be given by different irreducible components, all of them smooth, and that meet over the hyperplane sections of a certain coordinate system. So it's going to be like x1, x2, x3, up to xr equals to 0. That's how this guy is going to look like. And usually you want the transform of the singular locus to be here a simple normal crossing divisors. And since you want to have more control, you might want to use this along the process. you also add here a simple normal crossing divisors to begin with, and you're going to say that everything here needs to be compatible with these new divisors. So what does compatible means? It means that you want to consider composite of blow-ups, but you want every blow-up to preserve the fact that this E is a simple normal crossing divisors. So you add a condition to the blow-ups. You ask them to be E-adapted or E-compatible. So essentially, this means that if I have a divisor there, I only want to consider, so if I have a divisor, I want only to consider centers which either meet transversely or they are contained, or which are points in the two-dimensional case. I do not want to consider blow-ups of things which are tangent. This would not be an E-adapted. So it means that at a certain coordinate system, not only my divisor is given by these coordinates hyperplanes, x1, xr equals 0, but also in the same coordinate system, these centers are given also by some of these x's and possible the other ones that are completing the coordinate system equals to 0. Now, when we do this, we also want something about y prime. As we said, we want something about the transform of the singularities. So we want also that this guy is E-adapted. I want also the restriction, or E prime adapted in this case. I also want the restriction of the exceptional divisor over y prime to be a simple normal crossing divisors. So I add this condition, so that when I can take the restriction, I still get the same property over it. Now, this has to be a little bit changed. I can say that this is going to be E compatible. I need to add a little bit of results or to the definition of what functoriality will mean. It will need to take care or respect the fact that you have a simple normal crossing divisors. So the result that I want to work with today and present the consequences is going to be a version of this theorem, but where we're going to have a foliation too. So let me just state here that for us, F is going to be a foliation, it's an analytic foliation. So although this is a conference that everyone might, okay, I'll just give the definition here. So I'm going to consider actually something, because it's not completely standard. I'm going to consider a subsheaf, but I want to take the subsheaf of the logarithmic derivations, that is the ones which are tangent to E. There's going to be a small difference between what I'm searching and what is normal. And I'm going to ask the usual things, that it's involutive. And also so that we all know what a strict transform means and how to transform, so I want some sort of saturation. So since I want to work here, I want saturated or log saturated. So I want this guy to be torsion free. So in other words, if you forget about the log here, I'm just asking for the singularities to be of codimension 2. That's the only thing I'm asking. And with the log, we're going to see examples of why I'm taking this log. I just want to present one of the definitions of class of singularities that we're going to work with, and it's going to depend on the log. But you can, for now, think of the usual definition of foliations, right? And in this setting, so we have saturation. What we're going to do here is that if we add here a foliation, I'm equally going to add its strict transform. So since I have a notion of saturation, I also have a notion of strict transform, just as in the usual sense. And now the SPI is going to be a locally finite composite, not of just blow-ups. I will need to add weighted blow-ups. So this is the point that this x prime will become an orbifold. And I want some compatibility with the notion of foliation. So I'm going to say that they are F-aligned. Now, in the same way, I want my y prime to be well behaved in respect to my foliation. So I want it also to finish up with something which is F aligned. And here I should also add some sort of F compatibility to the statement of canonicity and functoriality. So this is the theorem that I want to present to you. And its consequences. So the main statement of the theorem, the thing that I feel like is the heart, the technical heart of the theorem, is the condition of being the centers being F aligned. And of course, this guy.
Proving the singularities of F in any way, right?
Sorry? No, I'm not claiming that. For now, I'm just saying that something is compatible with F. I need to explain what compatibility means. So one of the first things I'm going to do is to explain what this means. And then I'm going to come to how I want to use this to resolve foliations. Because this is my principalization type result. There's no ideal to principalize, but there's a subvariety to resolve. So it's a consequence of principalization that I'm using here. So let's just state here that the singular locus of F, possibly with the log, is going to be all the points in F where d log divided by F is not locally free. So this is this is the definition of singularities of a foliation with all the log here. It's just the usual definition. I'm just considering the log here so that we can talk about F is log smooth. If this guy is empty. So let me start by giving you an example of what this means so that we understand what this log here is playing a role for. Now let's consider the case of a saddle node. So I'm fixing C2, and I'm considering here F generated by the vector field x dx So if we draw the real picture, what we're going to see is that there is a central manifold. This is going to be the axis x, and this is going to have a flat contact, like an exponential of 1 over x, exponential of 1 over y in this case. It's going to be like an exponential of 1 over y, this kind of graph that is appearing here. Now, if we consider the notion of singularities of this f, we know, oh, it's when x and y are equal to 0. So the singularities of f, well, this is 0, 0. It's also saturated in this sense. There's no codimension 1 singularities. But we can, if we add different kinds of exceptional divisor, this notion is going to change slightly. So first of all, if we consider this as being x equals 0, so if our divisor is x equals 0, now I'm claiming that this is empty. Right? Because now dx log in this situation is generated by x dx dy. So if we consider the quotient here, like this, the x dx is here too, right? So this is also generated, if we prefer, by x dx plus y squared dy. So when we take the quotient, there's only going to be one, we're only going to need one generator, the one coming from dy. So this is going to be locally free, and we're going to obtain that the singular locus is now empty. Now, and the same thing will happen if we consider x times y. Right? If x, so let me just note this, if E is equal to x times y, then again, is empty. But if we consider E as being y equals 0, now this is not enough. Because for y equals 0, there is a y square here. So y dy, when I take the quotient, is still going to be an element coming from y dy to this quotient. So in here, again, the singular locus is going to be 0, 0. So it really depends on which exceptional divisor we have. We're going to have a different kind of singular locus in respect. We're going to have that it's either log smooth or not. Okay. So this is going to be one of the notions of singularities that are going to be considered to be as simple as possible for us today. It's going to be the log smooth foliations. Now let me enjoy here by already pointing out one class of singularities, or one class of foliations, that I can already tell you what we're going to do something about them. So one special class or type of foliation that already appears in all of the talks are the algebraically integrable foliations. So let me just consider the following. We'll say that f is totally integrable if there exists phi from x to be dominant meromorphic such that f is nothing but the relative differentials in respect to this guy. So these are generated by the deltas in the x log such that d of f phi is 0 for all f in OB. So you take any pullback of a function in B and you want to make it 0 by the derivatives, right? So you can think of just taking the level sets, and the leaves are going to be just the level sets are going to be unions of leaves. I'm taking all of the derivatives which are tangent to the level sets of this morphism. And if now that I recall this definition, I want to claim that this result, as we are seeing here, already is going to give us one corollary, which is that so the corollary works for more general classes of foliations, which I'm not going to present the definition. Foliation. There exists a proper bimeromorphic map. So x prime, f prime, e prime to x, f, e, such that f prime is log smooth and something even more monomial. So I want to comment about these theorems, but let me comment about the hypotheses that appear here, which I'm not, or the conditions that appear here that I'm not really going to talk about. First, Darboux first integrals is slightly more general than this. So you have transcendental leaves. You can think that locally this morphism phi can have powers, or the elements of it can be powers such as x, or functions such as x times y to the power pi, or some transcendental number. So it is slightly more general than the situation that we are looking at with totally integral foliations. I don't want to comment on how to do things in this setting. It demands more technical details, so I'm going to simplify. Just state if you know what it is, it's good, but if you don't, we're going to focus on this case. And the second thing is, what does it mean monomial? I mean, if you think about this, we are looking at a morphism, so you can think about what is the simplest kind of morphism. So we do have, for instance, resolvable resolution of morphisms that leave the morphisms to be semi-stable. So essentially something which is, at every one of the entries, a monomial. So there is a condition also for the foliation that does this. It becomes the level sets of a morphism which really look like all the entries are just monomials. This is what is behind the word monomial here. I'm not going to give the precise definition, but this is where it's coming from.
So they have negative and positive exponents?
Yes. No, good point. We can always make it always, the monomials can always have positive exponents. You can always do that. You get rid of the decritical components. Yes. Good point. Good remark. So before continuing, let me just make a couple of comments about the literature of this. So previously, so as I said, the resolution of singularities goes back to Hironaka, and then in the analytic case to Hironaka, Rocca, and Vicenti. Now the idea of using weighted blow-ups in this setting come to two recent results of Abramovich, Temkin, Vodarchik, my collaborators, and McQuillan, independently. And in both of these cases, they worked without exceptional divisors. No exceptional divisor. Now these are results. This is 25. It appeared in 20. They were both at the same. They appeared at the same time in arXiv. It just took longer for ITW to publish theirs. And here I think it's 23, the year it was published. But they go back to 2020. Both of them they go back to 2020. So this was resolution of varieties by weighted blow-ups. Now with E, there is a work of Jarek and of all of us together with Queck. So these are two preprints, again, that now with E, with the exceptional divisor. And the method that we have here is basically this case here where f is just the derivatives, all of the logarithmic derivatives. So it's a special case of this guy here. So this is for the weighted. Now foliated. If we think about the foliation that is here, then first result was always without weights, goes back to my thesis. So it was rank of f equals to 1, and it goes back to my thesis. This is the result I was saying that I told Frank. And local uniformization. So the local result goes back to 2016. And I think I want to just mention that this corollary, so the local uniformization of Darboux was also a result of mine from 18. But the big thing here is that with the weighted blow-ups, we are actually able to do things in a global way in both theorems. So let me explain more about this result. Now that I talked about the literature, let me put here the years too. This is 23 and this is 25. So the first thing, the thing that I need to explain now is the heart of the theorem. What is F aligned? And to simplify my life, I'm going to take E as being empty, so that we don't have exceptional divisor. I can just care about the foliation itself. If you know how to do E adapted, you'll need to add the same kind of conditions here. Okay? So a center of blow up is F aligned if for any point A in the support of J, so where it lies, there exist coordinates, Euclidean coordinates, or in the case, yeah. Good point. So I'm leaving this, good point. So this is going to be a Reis algebra. But I'm going to start the presentation as if it was an ideal. Okay? I'm going to start off thinking of J as an ideal. So this is why I'm putting. So for now, let's think of an ideal sheaf. So there exist coordinates, x1, xr, y1, yn minus r, such that, so I want two things to happen. First, if we're thinking about the ideal, I want to consider, so I'm going to first think about it without being a weighted center, just a usual center of blowing up. So this is just coming from an ideal. So if it's coming from an ideal, I want it to be given by certain coordinates x. All of the x's up until r, the same r which is here, these are going to be special coordinates, and some of the other ones. And probably I want a bit more space. So I want it to be given in this way, just as a usual blow up, a smooth blowing up. And I do want some presentation of f in these coordinates. I want f to be given here by dx1, dxr. So these coordinates here are very special. They are the transverse coordinates to the center, the transverse part. And I'm going to have other derivations. And these derivations are going to be the extreme opposite of being transverse. They need to leave my center invariant. Such that f of k is contained in k being just where k is just the part that depends on y. So this is already enough to talk at least geometrically about what is F aligned. So if we think about in C3 and say that we have a foliation given by dz equals 0, then essentially you're going to have the situation that either your center is going to be, say, contained, or it's going to be transverse to all leaves, or just a point. So this intermediate case is the case that you do have one coordinate here, which is getting out of the foliation, one that is inside the foliation, that's going to play the role of the dx. So we can think that here is dx1 and dx2. And the center here in purple, if we consider this center here, the C1, C1 is given by x1, z, and the foliation here is given by dx1, dx2. So this is perfectly fine. So if we take away the x1, this is going to be invariant. So this part, just this part here, is the k. And this part is going to be invariant. So you're able to decompose your center in two parts, one that is completely transverse to the foliation, and the other which is the extreme opposite, which is invariant. This is what I want to demand for it to be F-aligned. Now, since I need to do this for weighted centers, the way to present a weighted center is much simpler. I need to consider weights in respect to each one of the coordinates. Now, there are many ways to try to present this. There are at least 3 ways in the literature. Personally, I prefer the way that comes back to Villameor, coming back to Reis algebras, and that was worked a lot by Jarek, and that consider this not as an ideal, but as a Reis algebra over OX, and where each one of the coordinates here, we need to consider a dummy variable t, which plays the role of the algebra. Now, if we consider this, this is the Reis algebra associated to the ideal x1 to xr, y1 to ys. And if I want to add weights, I can add the weights to the dummy variable. So I have 1 over a1, 1 over ar, 1 over b1, 1 over bs. Where a, I, b, j are natural numbers. These are going to be our weights. And that's it. That's what all I want to do. And here I'm going to have the same thing. I'm going to have the Reis algebra. So, and I want to take also the integral closure here, sorry. I want always to work with the integral closure so that I have unicity of the object that I'm considering. So this is how we're going to present a weighted center, and then the definition is going to be just the same as we just discussed it here. And just to point out, a known example of a F-aligned blow-up is a blow-up where the center is tangent. And now to these remarks that we made here, the importance of this notion is exactly that it allows us to preserve a good property of the foliation. So once you have this little proposition here,
Can you assume it as a quotient algebra or a subalgebra?
a subalgebra of this one. But it's just the one, it's a subalgebra of this one, but just generated by the y's, and you take the integral closure. So the proposition that I want to say here is, if we take a blowing up which is F-aligned, F-aligned, then if F had some nice properties, so if F is log smooth, or say monomial, then F prime is also log smooth. Monomial. And this is part of the idea of this main theorem here. Since we know that we are able to resolve singularities of subvariety by this kind of blowing ups, if we know that in the beginning we had already a foliation that was nice, then so will be the F prime. So this is the first remark that I want to make about how we are going to apply the theorem. And it's the last remark I want to do about F-aligned. This is what we are really going to use later on. Now let me talk a little bit about resolution of foliations. So the problem, in some sense, the goal, is find x prime, f prime, e prime, just as before, proper bimeromorphic, such that our f prime here is as simple as possible. Now, this notion is absolutely vague, right? So one of the first things I want to do is to say, what does as simple as possible should mean? So if the rank of the foliation is equal to 1, if it's a vector field, then these are called elementary foliations, or elementary singularities. And this is a notion that goes back to the linear theory of Poincaré, the classical case. If we have corank of f equals to 1, it's a much more recent notion, is the notion of simple singularities that goes back to a paper of Cano Cerveau. If you do have something like Darboux first integrals, then monomial plus logarithmic should be your minimal type of singularities, the one the most reduced, as simple as possible that you can do by blow-ups. And in general, there's no conjecture. We don't know. Now let me briefly make a comment about logs move. So I presented something at least that was valid for arbitrary foliations. But recall that there is the example of Euler. Which is just very simple. And very close to the case that we just presented about the saddle node. But now the axis where you do have the central manifold is formal, is a formal curve. And then you have this flat behavior around this formal curve. Now, as we saw with the saddle node, what we really want to add for the log structure is the central manifold, is the x equals 0. But now it's just a formal thing, so you cannot add it. And if you try to add the y equals 0, this is not going to be enough, as we noted. And such a thing will not improve no transformation improves this picture, improves it. Because every time that you blow up, you're still going to have a saddle node coming from the street transform of the central manifold. And again, you're going to have the same central manifold that you would like to add to the log structure, but you can't. So this cannot be done better. So log smooth is not general enough for arbitrary foliations. But in any case, there is the notion of, okay, so if we do not know what we're searching for exactly or yet, we might want to work with some other notion or find appropriate classes of singularities that we can control. So say the logs move ones are such that we're going to be able to control because of this result. The monomials are going to be the same, but you also can talk about other classes. So let me briefly mention that we're finishing up to write a paper with Colin Spicer and Dan Abramovich, where we're going to consider there's the case of simple singularities of corank 1, but there's also other singularities of interest to the MMP community, in particular some subclasses of log canonical foliations, which should play which we believe is going to play an important role. But for now, I just want to make this brief comment that we're finishing up this work. Now, the point about the literature of this problem. So if the dimension of x is 2. This is the classical Bendixson-Seidenberg. From 1901 and 64. If the dimension of X is 3, then this goes back to works of Cano Cerveau, or Cano Cerveau and Cano. So this is 92 and 2004. And Panazzolo, McQuillan, Panazzolo. So this is 2006 and 13. So Cano Cerveau is for the case of co-rank 1 foliations which are not dicritical. The general case in dimension 3 is from Cano. Daniel does the case of Rio analytic vector fields. And for the complex case and the algebraic case with McQuillan in 2013. And something very special about this case is that we need weighted blowups. In the work of Daniel, and for vector fields in dimension 3, it's already in the case that we must have weighted blowups. Now there are other results in dimension 3. There is a result without weighted blowing ups, but with more general final normal forms of Cano, Rocha, and Spivakovsky. There's also the case of complete vector fields by Helena and by Julio, which are, I lost Julio, but he's here. Helena is there, by Reis and Rebelo. And for dimension which is bigger, there's very few results, and they are mostly local in nature. So they're either local uniformization results, there's a result of Duke, Cano Duke, there's my result there that we cited, or they assume something about the vector field, so there's the work of Cano, Sad, and I forgot the third collaborator, so maybe Camacho Sad, which is also adding something which is very local in nature, which is to suppose that the singularity is absolutely isolated. So the problem is open. Okay. So the fourth part is I want to give you the idea of the proof of how the theorem implies the corollary. Because this is the key to understand how we want to use a principalization result to try to prove resolution of singularities of foliations. So let me add an extra hypothesis here. Again, to simplify my life, I'm going to assume the exceptional divisor is empty, and also that phi from X to B is an morphism. No indeterminacy. So recall that we're trying to prove this result. So we have something which is totally integrable. As I said, this was a meromorphic map to a base. I'm assuming that it's actually going to be just a morphism, no indeterminacy, and then there's no exceptional divisor. Now, the setting that we have will have three main parts. The first one, or the 0 one, which is the setting part, I like to call it embedding. So I want to consider here Z given by X times B, and the subvariety Y given by the graph of phi, and the foliation H defined in Z given just by dx times 0. And know that this guy here is certainly going to be smooth, so it's a log smooth, right? It's just dx, x is a smooth variety, so this is log smooth, orthogonal. And the remark that I want to make here is that if we consider the restriction of h to y, then this is f. And if you think about this is just giving you that h is given by the forms dw, where w is a coordinate of B. It's one of the zero locus of this B. And when we restrict to y, so when we restrict to the graph, this is essentially going to be d of phi of x. And d of phi of x is essentially f. So of course you have to make this argument precise, but this is the idea behind why the restriction is f. So we're just putting ourselves in this setting, and now we gain something because we went to a bigger setting where now our foliation is really, really nice. So the first point is going to be apply the principalization theorem. So we get some sequence of blow-ups, z prime, y prime, h prime, e prime, sigma, z. And since we had only done f-aligned blow-ups and h was log smooth, so will be h prime. Or monomial. And finally, we restrict. We also know that y prime is f-aligned. And from this, we are actually able to prove that the restriction is also going to be log smooth and monomial. Then I'm going to call f prime is log smooth monomial. And now, the morphism that you have here is simply going to be the restriction of sigma to y, or to y prime. And this is going to be our proper Birman-Marshall morphism, such that the transform of f is going to be this f prime, which now is nice. So this is the idea behind it. You transform the problem of resolution of foliations into a double-step problem. One that demands some sort of embedding or pullback. You apply the theorem to keep the singularities good enough, and then we restrict to obtain the result that we intended. So I don't have time to comment, but too much, but I do have 2 minutes. So let me just say that this can be generalized to much more general classes of foliations. So in particular, we only used here that was log smooth. So actually you can have a version of this theorem for relative resolution. So if you have a pullback, so if f is the pullback of a log smooth foliation, you will also be able to transform into a log smooth foliation. So since I only have 2 minutes, I don't think I'm going to enter this. And I'm just going to finish with maybe a question, because I think that I'm not going to enter the relative version. I'm going to stop here with the theorems, but I want to make a question, because I've seen that for the last 6 months, I've seen many talks talking about extension of foliations. And I wonder if there are also results about extension of foliation, say from a subvariety of Pn to Pn. I only need something even weaker, right? From the subvariety to the normal bundle, where the extension is now nicer. Say, for example, that you have a corank 1 foliation for which co-rank 1 foliations can you find an extension to the normal bundle, which is going to be a codimensional co-rank foliation, which is simple. For those foliations, you can apply this kind of result directly. And in the general case, you hope to be able to modify first your foliation to afterwards attack this kind of embedding problem. So I'm going to finish this with this problem because I've seen many, many talks in the previous 6 months about this. Today there was one somehow that used also from Alan, right? So if someone has an idea of how to do or how to advance this, I'll be very interested in discussing with you this week. So thank you a lot.